theory, which you should know. It's your culture. It's the flagship program of UK mathematics, or it was in the 80s. The times have gone down since Atiyah died, but okay, we'll compensate for it using celestial holography and applications to scattering amplitudes. So, yeah, I'm going to change a bit track now for a bit, and I'm going to focus for this and the next lecture on celestial OPE mainly, that Prahar mentioned a bit, but I'll give you more details about that kind of thing. Okay, so firstly, in the last lecture I showed you how twistors are applied to this classical problem of solving linear field equations. Now we want to show how twistors can be applied to solving interacting problems, but we're going to go through it by means of celestial holography, by the route of celestial holography. So firstly, let me try to tell you what amplitudes look like. I think all the other speakers have basically spoiled this for me. For some reason, everyone kept telling you how good amplitudes are and telling you that I would tell you, but okay, I will tell you now. So you know how ugly Feynman diagrams are, so you would expect that if you just try to add Feynman diagrams in Yang-Mills or, God forbid, general relativity, you would get some sort of exponential madness, and you will not be able to compute anything, say, beyond 4 points that you do in your classroom. But it turns out that that's not the case, that there are many hidden mathematical structures in the amplitudes of massless particles like gluons and gravitons that show up only in the final answer. And we know this very well in the flat space case. In cosmology, people are trying to develop the same magic, but they haven't found it yet. Well, they have found traces of it, I guess. So what's the magic? Take an endpoint amplitude of massless particles, massless spin one, gluons or gravitons basically, massless gluons or gravitons. I'm going to focus on giving you the expressions for the simplest tree-level amplitudes, which are called the maximally helicity violating amplitudes in this lecture. As you start going away from that subsector of amplitudes, they start becoming more and more complicated. Anyway, to write down the amplitude, you start with n massless particles. There are no momenta. Now I'm going to represent them as ki. I runs from 1 up to n. In spinor notation, I can decompose them into some spinor helicity variables. Since I use lambda as my abstract coordinate on twistor space, I'm going to call these kappas and capitildas. Kappa I and capitilda I alpha dot. It turns out that scattering amplitudes, at least tree-level scattering amplitudes, can be very naturally written in terms of spinor contractions of these variables. So, for example, all my amplitudes will be written in terms of these spinor brackets, which you might recall were epsilon, and I can mention beta alpha, kappa I alpha, kappa j beta, and the square bracket, which was. So now instead of writing kappa I, kappa j angle bracket, I'm just going to write ij, because I'll always have these labels floating around. It will be unambiguous what I mean by them. J. There you go. And the amplitude will naturally get expressed in terms of these objects. So, example, the famous poster child example is the Park-Taylor formula. And, well, Taylor is still active in celestial holography, in fact. So the Park-Taylor formula tells us that the MHV amplitude, so I don't want to write it down, it's maximally helicity violating. But basically, it's an amplitude that involves 2 negative helicity particles and n minus 2 positive helicity particles. So in the gluon case, suppose we take an amplitude of gluons 1 and 2, in which gluons 1 and 2 are negative helicity, and the rest positive, n plus. So let me use a different bracket here. There is a notion of something called a color stripped amplitude, where you don't write the gauge group factors just yet. I'll write the whole thing in a sec. This, up to some gauge group factors, the amplitude is given by a very sweet looking expression. This is 1 to the 4 in the numerator divided by a cyclically symmetric denominator. 1, 2, 2, 3, 3, 4, all the way up to n1. The point being that if instead of 1 and 2 you took some other arbitrary pair of particles r and s to be negative helicity, they don't even need to be adjacent. All that would happen is that the numerator would change. It would become r comma rs angle bracket here. And now the full amplitude is basically just this, but with some color factors attached and some permutations taken over how the various gluons are arranged in the denominator of this cyclically ordered object. Full amplitude is both symmetric, so you can sort of guess that you have to do some permutations, up to attaching appropriate color factors here. So permutations sigma in as n minus 2, certain structure constants, so A1, A2, B1, B1, A3, B2, and so on, up to, I don't know, B something, AN minus 1 AN, and then you have to permute these. So, I should have written sigma acting on some indices. Sorry about this. Sigma of A3, B. Sigma is a permutation of n minus 2 labels. Sigma AN minus 1, sigma AN. This is just a bunch of color factors which you might recognize shows up in amplitudes, and then you have that Park-Taylor object. Sigma 3 up to sigma 1. So it's just that. If you compute this, and it's just that for arbitrary number of gluons, that's the magic here. If you try to compute this at 4 points, if you try to compute this at 3 points, you have one contact term to compute, you'll get the answer within a sec. Try to do this at 4 points, you'll take 15-20 minutes, half an hour, something like that, if you know how to work, if you have worked with Feynman rules recently. Because there are like 4 diagrams to consider. You can get away with using gauge choices and stuff to quickly get the answer. If you try to do this at 5 and 6 points, you will see the pattern emerging, but you will very quickly start getting of the order of 100 Feynman diagrams. Of the order of 100 terms when you add all the Feynman diagrams together. And it will all sort of reconverge into the same thing. I forgot to write the momentum conserving delta function, but in celestial holography literature and all, we usually put that in the amplitude as well. So let me just put that in. So there's a 4 momentum conserving delta function that just imposes your favorite momentum conservation. So the question now is that you know from experience that whenever one has a complicated calculation that gives out a very simple answer, there's always some kind of dual formulation or something hidden deep somewhere else that sort of is generating this simplicity. This you cannot just get from symmetry or anything. This is a very complicated formula. You can't just get this from the symmetries of the problem. There has to be a genuine dual set of dynamics that has to give rise to this formula. And this sort of dual dynamics, the hope is that this dual dynamics is some sort of two-dimensional celestial CFT. The other sort of thing that works is that there is something called a twistor string theory, but that's a six-dimensional object that lives on twistor space. And just like I showed you earlier, you can take holomorphic data on twistor space and get solutions of field equations on space-time. You can also take a certain string theory on twistor space and give rise to amplitudes on space-time. So that's another dual formulation that we know works. And the question is, the big question is, can we relate these various dual formulations somehow through the triality diagram that I drew for you in the first lecture? We won't get to all that. In this lecture, I'm just going to extract some celestial OPE data from these things, and I'll try to see if some sort of celestial holography structure can be viewed through these twistor lines. And maybe if I get to twistor strings, I'll show you how this formula can emerge in a very simple way later on. Okay, so there's a very similar formula for the gravitational case. For the gravitational endpoint amplitude, the formula is due to Hodges. So endpoint graviton amplitude, graviton MHV amplitude also has a very simple structure. In gravity, the number of diagrams, not just the number of diagrams, but the number of interaction vertices themselves grow with the number of particles involved in the scattering. And yet, the final answer condenses into a very simple final form. So I'm going to denote graviton helicities by 2 minuses or 2 pluses. And the final answer is given by a very simple, well, there's a prefactor that looks a little bit like the Park-Taylor factor. 1, 2 to the 6, well, 1, 2 to the 8th over 1, 2 squared, 2, 3 squared, 3, 1 squared. And then the remaining amplitude organizes itself in terms of a determinant. So you get determinant of something called the Hodges matrix. So let me explain this notation to you quickly. The Hodges matrix is an n by n matrix with elements, very simple elements. So Hij, Ij runs from 1 up to n equals square bracket Ij over angle bracket Ij whenever I is not equal to j, and the diagonal entries look like, Prahar didn't discuss this in 4 dimensions, they look like soft factors. J not equal to I, Ij over Ij. Now there's a sum over J. So this is the diagonal entry over I, 2J. And 1 and 2 are just our angle spinors for 1 and 2. The negative helicity particles. 2i, 1i, 2i. And the idea is that you take this n by n matrix and construct the n minus 3 by n minus 3 submatrix by removing rows and columns 1, 2, and 3. So basically, just like you take a minor from a matrix, you remove rows and columns 1, 2, and 3. You construct this submatrix. This is an n minus 3 by n minus 3 matrix, and that gives you the graviton amplitude. And that's it. Up to momentum conservation, which I forgot to write again.
So I'm convinced by the role played by the 3. I guess you have to do the permutation, so everything will be 3 dependent. But why is it 3? I understand the 1 and 2 because of the negative releases and so on. But why is the 3, which is next to stupid question? Why is the 3 special? Well, because it goes because the first adjacent. I think you have to sum of 3.
3 is not special. You can, instead of 3, you can choose any of the other positive
and then you
ST.
sum over all the possible. You do the permutation.
No. They're all equal.
So this
As long as you replace the 3 in the prefactor by that other positivistic graviton, and you replace the 3 in the removed rows and columns by some rth row and column,
right.
Along with the prefactor, the whole determinant times the prefactor is equal.
So you could have called it like R.
It's some hidden symmetry of this object.
Nice. It's not obvious because.
It's no way obvious.
Yeah.
You can check it by properties of determinants, adding rows and columns to each other.
It's easy then. It's just a crossing zim. I would say it's like, I don't know, looks like crossing zim, no?
I have no idea how crossing works at high points, but this is actually secretly you can prove it just using properties of this determinant. I don't know if it's crossing. I don't have intuition for crossing at high points.
And then if I compute the determinant, because it was explained, is it the rest is also squared now? 3, 4, blah blah, and 1 squared, no?
Yeah.
So it's a double copy, you can explore it.
Oh yeah. You will very much see some kind of, well, 2 different color-ordered amplitudes take a product of 2 of these gluon amplitudes. They might not be the same amplitudes. You won't always get a square, but you'll more generally get a product of a gluon amplitude in some ordering, and another one in maybe slightly permuted ordering.
So not really a square,
And then sum over some of those linearly, and you get the answer. But the point is, that's the answer. Even double copy doesn't give you that. That answer is even more deeper than double copy. Double copy will give you something which you still have to like permute over loads of things. And when you want to permute, your answer will have a complexity of the order of some n factorial or n minus 3 factorial. That answer is a determinant. Its complexity goes like n squared, n minus 3 squared maybe, the complexity of evaluating that determinant. It actually is very, very deeply related to the self-dual. This is very close to just being an amplitude of positivistic graviton, so it's very close to the integrable subsector of gravity that's called self-dual GR. So this is like a manifestation of that being very close to integrability, that you get this extra simplicity in this answer.
So you're saying that at the end of the day, only some polarization actually to matter when including this.
Yeah.
This image, yeah.
If you start taking more negativistic gravitons, the structure, it is still some sort of determinant. It becomes more and more complicated, grows more and more complicated as you start increasing the number of negativistic gravitons. You had a question, right?
Yeah, just about notation. In these amplitudes, are they the ordered amplitudes?
No. That's why I put a square bracket here, and then the full amplitude, the order summed amplitude is that one. I just wanted to display the color factors at least once because I'm going to write the celestial OPE, and that's where the color factor comes from. And this amplitude is not, the graviton amplitude is unordered. It's fully both symmetric.
About like, okay, so there's no, that's not the ordered amplitude.
No. You can check that up to that factor of 1, 2 to the 8th in the numerator, the rest is actually completely permutation symmetric. It's not obvious in the way I've written it here, but it is. There's loads of magic. So one would hope that this thing might secretly be related to celestial holography. We don't know.
The n minus 3 removals, am I correct around those do correspond to physical symmetries? As in, you normally remove 3 rows and 3 columns because otherwise you get a vanishing determinant. One of them normally corresponds to momentum conservation. I think one of them is then a Shelton identity.
You don't need momentum conservation.
No, but as in, if you don't remove any rows and columns, you take determinant vanishes, and the vanishing determinant gives you momentum conservation.
That's probably true. Yeah. Maybe.
I know that scattering radial HCs do similar things.
The thing is, I've chosen these. Usually, some reference spinners sit here. I've just chosen these to be 1 and 2 for simplicity. If you take general reference spinner, then you probably need to use momentum conservation for the determinant to vanish if you don't remove the third row and column. But I think if you choose just 1 and 2, then it vanishes identically.
You've chosen 1 and 2 in reference spinners.
Yeah,
That's
because
not related to the fact that you remove 1 and 2. You can just pick.
it's just the most natural choice of reference spinners because 1, 2 negative velocity gets picked out. This is the answer that Amplitudes string most naturally also gives. That's why I usually always work with this choice. Anyway, I want to do a little bit of celestial holography. I wanted to show you the amplitude because they're cool. What we're going to do is we're basically going to extract their collinear behavior because we want to study the operator product algebra of celestial CFT. So celestial holography, as Prahar was explaining, posits that you have some kind of conformal field theory living on some two-sphere, which we hope is the celestial sphere in Lorentzian signature, but in this more general complexified case, some abstract two-sphere that is related to the spinor-Helmholtz variables. And the hope is that there's some is there a 2D, okay, this is section 4.2. Celestial CFT. Now, our dream is that there is some 2D holographic dual this is our dream that reproduces 4D perturbative quantum gravity or perturbative quantum field theory, Yang-Mills, stuff like that. And concretely, you would like to have some operators in this dual celestial CFT. So some operators, say some gluon operators, which might have some adjoint indices, which live at some, so which are functions of the spinor-Helmholtz variables, or some graviton operators with the plus or minus labeling the helicity, and in this case A is the adjoint index. And the hope is that one could construct, if one day we find celestial CFT, one could construct the correlation functions of these operators independently, and presumably that would be the easy way to calculate those beautiful amplitudes that I wrote down earlier that you can't do by finite diagrams. Okay, so, but today we will not realize that hope because we are failures. We will instead just be happy by trying to construct the collinear behavior. And I'll show you that you can build sort of toy models of this OP algebra in Twistor space through which you can actually very easily construct this collinear behavior. And it genuinely behaves like a two-dimensional theory. It's just that it'll live on one of these twistor lines rather than a celestial sphere. It'll live on this chiral celestial sphere, you could say. So, towards doing that, towards setting this up concretely, what we can do is, firstly, we'll fix little group scaling. In Prahar's lectures, we usually fix little group scaling everywhere. So what we're going to do is, on celestial sphere, I'm just going to fix it slightly differently from Prahar, or from the literature. What I'm going to do is, I'm going to take kappa, the angle spinner, the end-ordered spinner, and I'm going to think of this as living on an affine patch of my sphere, of my celestial sphere. Basically motivated from the fact that that's what Twistor space instructs us to embed the celestial sphere as Zi for I running from 1 to n. So I fixed my little group scaling by setting the first component of kappa I to 1. And the kappa tilde components will remain arbitrary, non-zero arbitrary data. 1 dot, 2 dot. And now the operators look something like OA plus minus Z kappa tilde and plus minus z kappa tilde. Concretely, we want to say that correlation functions so let me write the gluon example. We want to say something like this. The correlation function of n of these operators, I running from 1 to n, O, ai, helicity, ji, zi, kappa tilde I, should equal an amplitude involving particles 1 with helicity j1, 2 with j2, and the associated gauge indices, which I'm just suppressing for simplicity, jn. This is the conjecture. Well, the sort of dreamt up conjecture. But even if it's just a dreamt up conjecture, we can still try to find consistency conditions. Okay, what are the properties of my amplitudes that I can translate into some CFT properties of these operators? Are there any properties of the amplitudes that look like they're properties of CFT correlators? Prahad already showed you loads of these. He showed you that the soft theorem looks like a CFT word identity. What I'm going to focus on is the collinear behavior rather than the soft behavior. I'm going to show you that I'm going to tell you mostly that behaves like a CFT correlation function. And this becomes quite manifest with the Spark-Taylor formula quite easily. So, well, might go 5 or 10 minutes over time, but if someone is dying, or you can tell me. Anyway, so with the Spark-Taylor formula, let's just consider the collinear behavior. Okay, firstly, let's write down the Spark-Taylor formula with that little group fixing. Little group fixed Spark-Taylor formula looks like 1, 2 minus just the color ordered object, just this ordering, this thing. Can someone quickly tell me what it looks like with that little group scaling? Can someone quickly evaluate these angle brackets and tell me what an angle bracket ij is? You know. Okay. The Zi minus Zi. Huh?
You looked at me.
Okay, so this is, I'm going to shorten it to Z subscript ij. If you don't see why, take it as an exercise. It's super simple, just the definition. Epsilon, yes. Yeah, or you can write it as a determinant if you like. It looks something like 1 over Zj, 1 over Zi. Anyway, there are various ways of calculating this. And now this looks like a 2D CFT correlation function. So you get Z12 to the 4 divided by Z12, Z23 up to Zn1 times the momentum conserving delta function, which you can't do anything about, which is still a mystery to most people. So K1 up to Kn. At least the actual amplitude looks very much like a CFT correlator, or at least the denominator of it has the correct poles that you expect from the poles when two operators in a CFT collide.
But the numerator doesn't really look like, CFT.
Yeah, the numerator is very, numerator is super weird, and I don't think we still know properly how to sort of get the numerator.
Yeah, I've seen, there's some similar things in other contexts, completely different contexts, but the numerator maybe some kind of look like background charge or some modifications, not really the pure vacuum. Completely different context, but it looks like, I'm not saying it's the same. It's like it can happen that you have CFT correlators that are actually slightly modified in a different background with some background charge and stuff.
I think somebody has tried doing that. So one of these, I think Tomas Taylor's group has tried studying celestial amplitudes that are defined with the inclusion of some background charge. And that seems to cure this that seems to give an understanding of this. It also seems to cure the problem that gets rid of this momentum conservation. So it's really makes it look like a CFT correlation function. So maybe, yeah, maybe that is the right track. But at the moment, I'll just focus on what I know best. At least for the positive helicity gluons, this has poles as all the positive helicity gluons collide with each other. This doesn't have the pole, so I wrote it like that, but secretly it's just that. So it doesn't have the pole where 1 and 2 collide with each other. So that behavior is still mysterious. But you can, so in that, when 1 and 2 approach each other, there is no singularity in this ordering as well as in the full formula. But when two positive helicity gluons collide, there is genuinely a singularity which looks very much like a CFT singularity. This is again a hint that there is some chirality in the system that is showing up.
Why do you say it's mysterious that there's no pole when Z1 goes to Z2?
Mysterious from the CCFT perspective, that there is no singularity as two negative helicity gluon operators collide.
I mean, there's quote unquote a singularity, but the coefficient of the singularity is 0 because the lower point amplitude is all plus amplitude, and that just happens to be.
Yeah, but that's an amplitude perspective still, right? I'm just saying from a CFT perspective, it's slightly unnatural to have completely regular OPEs. Okay, it's not unnatural, it's perfectly fine, the CFT.
No, we're not saying
Yeah,
that
I guess.
it's completely regular because we're only saying that there's no pole in this particular correlation function. That doesn't tell us that the full OPE that will never have singular terms.
Yes, so in
When
the
you
MHV
survey
sector,
this
you mean?
correlation function,
Yeah.
it will not contribute.
So, yeah, exactly. So in the MHV sector, when you have only two negative helicity gluons, the OPE of two negative helicity gluons doesn't really contribute to this particular amplitudes. Why? That is a mystery. Exactly how you compute it, but at least for the like helicity case, just the plus case, it's more clear that you can extract some sort of an OPE structure.
But usually when you have a correlator thing, if you look at some channels and you look at the OPEs, actually the OPE channel and things, maybe you can get information on the fusion rules of the CFT.
Yeah.
So maybe this is telling you that the fusion rule is somehow dependent on the density of the particles that and is 0 and 0 in this case. Maybe.
Yeah.
Maybe. So
In
the
the-
OPE algebra literally of the.
What could be happening is that in the OPE there's a singularity,
Yeah.
but the coefficient of that singularity is an operator whose insertion in this particular correlation function happens to be 0.
Right. Yes. No, that's okay. I see. Thanks.
It doesn't even need to be regular.
No,
Right,
right.
okay, fair enough. Yeah, so we don't know what that operator is, I guess. So I'll focus on the plus case. So when two of these particles, so suppose gluons I plus and J plus approach each other so that Zij goes to 0. What I'm going to do is, since I'm doing everything chirally, I'm just going to think of this CFT as living on the sphere coordinatized by Z, at least in this complexified scenario. And I'm going to think of kappa tildes as some sort of auxiliary labels of these operators, some quantum numbers of some extra maybe symmetries of something else. It is translation symmetry, but you get the idea. So my CFT is going to live on the Z sphere. So I'm going to consider these singularities. And now if you write your momentum, ki dot kj, your null momenta, then the dot product of null momenta, again, you can take this as an exercise if you like. This is ki alpha alpha dot kj alpha alpha dot, which is ij. So you write each of these as spinor helicity in terms of their spinor helicity decompositions. Then the alpha alpha contract and the alpha dot contract. So you get that and that. And ij angle bracket is just zij, square bracket ij. So basically, in the limit as Zij goes to 0, this sort of expected OPE limit, this is the expected OPE limit in CCFT. In the bulk, the particles become collinear. So Ki dot Kj, well, collinear or like parallel or anti-parallel. So basically, you can visualize this in Minkowski space most easily. So you get Minkowski space, and you have some sort of celestial sphere here. You have some interaction happening somewhere, and you have two particles emerging from this interaction with momenta Ki and Kj. They exit the celestial sphere at points Zi and Zj, and as Zi and Zj approach each other, the momentum null vectors sort of become parallel, or if one of them was pass pointing, then anti-parallel. So that's why in the bulk, in Lorentzian bulk, it sort of can be viewed as a collinear limit. And collinear limits of scattering amplitudes are again almost as well studied as soft theorems. They're super useful in jet physics, I think. But in our case, I'm just going to read off the collinear limit from the Park-Taylor formula. If I have time. Maybe I don't have the time. Okay. I will just write down the expression, which is going to be a very viable expression if you look at the Park-Taylor formula. Actually, it's very easy to read it off. So you have O plus, the answer. Let me first write down the answer, then we can see if you have time. Z1, Zi, kappa tilde I, OB plus. I'm going to do the plus case. Parity reversal says that you can do the minus case, so this is by itself okay. The mixed helicity case is the case that I'm not going to study. In the plus case, the OP can be read off, something like this. Goes as F. These are the structure constants. Let me just use simpler conventions where everything is upstairs. Zij, Zi minus Zj, O plus C here, Zj, capital I plus capital J. That's the gluon celestial OPE. And how do you read this off from the Park-Taylor formula? We can probably discuss this more in the discussion session if you like. But the basic idea is very simple. The pole is already manifest. Okay, you have to read it off from the full amplitude. So I rubbed off the full amplitude. The full amplitude is where you reinsert all these color factors and then sum over permutations. One of these permutations has the pole Zij, where I and J are adjacent to each other. So that's where this pole comes from. The color factor comes from the gauge group color structure that sits in the permutation sum. And the only mystery, and okay, I've expanded around Zj, so that sits there as the parameter of my OPE. Where does this come from? This comes from the only tilde dependence that occurs in the Park-Taylor formula, that's in momentum conservation. So in momentum conservation, in particular, you'll have Ki alpha dot plus Kj alpha dot, which is kappa I, kappa tilde I, kappa j, kappa tilde j, where kappa I is 1 Zi, and this is 1 Zj, and you expand to first order in Zij. This is kappa j alpha, kappa tilde I alpha dot plus kappa tilde j alpha dot, plus order of Zij. And I'm only writing this piece is already singular in Zij of the least order. Anything else I write will be non-singular, so I'm dropping it as we usually do in CFT. I hope people have seen OPEs before in CFTs. and that's why the tilde. Yes.
So yeah, okay. So I wanted to ask about the tilde. The extra set of terms that show up over there.
Yeah.
Do we know whether they're holomorphic or not? Like how are you on the left hand side you've written O plus as a function of just Zi, indicating somehow that this is a holomorphic operator.
Yeah.
But that holomorphicity is in CFT plays a very strong condition. It says not just the singular piece, but every single additional term in that expansion is holomorphic. And that holomorphicity is super important in order to extract this OP from the original correlator. So if they're not holomorphic, then you can't extract this OPE from the original correlator.
That's true.
So anyway, my question is, do we know whether those whatever the non-singular terms are in the OPE, if they are or are not, what's the are they holomorphic or not in Zi and Zj?
So the terms that I can extract from the Park-Taylor formula in like perturbatively in Zij, those I can indeed write as holomorphic like expansion in Zij. I don't know if there are additional terms that drop out in the Park-Taylor formula.
The Park-Taylor formula is special because it has only the singular term. There's no other term that will show up.
Yeah, I don't think anyone has analyzed this beyond MHP degree anyway. The celestial OP, that is an ongoing thing. So that's why I was saying I think it's this simple and holomorphic only in the MHP case. In NMHV, one would expect to need to write an expansion in kappa in square bracket ij as well, and get some anti-holomorphic dependence expansion. Here, it turns out to be much more natural. If you just try to find a CCFT dual that might reproduce the Park-Taylor formula for you, it seems to be much more natural. You just treat the kappa tilde as a separate auxiliary dependence and just work on the chiral sphere of the Zi's. Of course, this is, as you well know, an ongoing thing.
And the, sorry, very stupid, make a mistake. The FABC are such a constant of
The gauge group
the gauge group of that in the bar.
of the Young melts.
Okay.
Yeah. And so this starts looking very much like a Katz-Moody OP
Exactly.
up to these extra auxiliary pieces. Okay, how much more time can I take? Okay. So for gravity, you have a very similar scenario. That's what most celestial holographers have been interested in recently. So in gravity, the celestial OP usually, this is sort of a color kinematics duality style happenstance, where this structure constant FABC gets replaced by some kinematic dependence on the square brackets. So the graviton OP, you can, I'll leave this as an exercise, this is too hard to do. You can derive, say using a 4 graviton example.
Before we move on, just a quick question.
Yeah.
These things happen for collinear limits of the amplitude, right? So usually in these limits, there are also divergences, like.
Yeah, all this is tree level, of course. Yeah.
Are these related also with soft theorems or not? Because in prior lectures we've seen that the infrared divergence that comes when you take the momentum of the massless particles that goes to 0 is related to soft theorem, and there are also this kind of infrared divergences from linear limits. Is there some soft theorem associated with that?
I don't know about this. I suppose you're talking about this fact that his infrared integrand was like a soft factor of sorts.
Yeah.
I don't know if there's some exponentiation of collinear divergences. Maybe Prahar knows.
Yeah. I don't know it in this notation, but those split functions that you define in amplitudes, they receive higher divergent loop corrections. But I think you're just doing tree level.
I'm doing tree level. It is expected that they would receive some loop directions, but do they like exponentiate into something nice, or
I don't know.
that's not known, I guess. Anyway, in gravity, the expansion looks something like this. Again, notice that I am only focusing on the like helicity case. So from just the formula, the matrix entries that I showed you, you have square bracket ij or angle bracket ij. That's exactly the object that now shows up here. The square bracket ij is as it is. I haven't fixed any little group component, little group scaling. Well, that is as it is. And the denominator is now zij, which is basically that angle bracket ij turning into zij again. And you get O plus zj kappa tilde plus kappa tilde j. That's the gravitational OPE in the like helicity, in the positive case. So I'm not writing down the mixed helicity OPE. They are, well, the leading terms, so to speak, are universal. There's a universality in the leading collinear limit, just as there is in the leading soft limit. So they are known, but and the reference. So you can take a look at the reference by the Harvard group. Monica Pate, Anna Maria Clariu, and Strominger, Yuan. I have a nice sort of overview of all of these various collinear cases along with the mixed helicity ones, and they sort of exactly show you how you start with the universal collinear behavior of amplitudes and how you define celestial operators and how you define their OPE and how you derive it. And they also Mellin transform it to go to boost eigenstates. I'm just going to stay in momentum space because it's just cleaner. We won't need to do the Mellin transform here. Okay, now to end the lecture, I want to talk about soft modes. These are all OPEs of hard celestial operators because they have non-zero energy. The energy sits in the momentum, and my momenta are completely arbitrary and hard, null momenta. To go soft, we want to do a soft expansion. Now this is again a property of the MHV amplitude, that the MHV amplitude you can basically Taylor expand it in the kappa tildes. It's slightly formal because you have a momentum conserving delta function. So if you prefer, you can go to Mellin space where the momentum conserving delta function goes away, or you can sort of put some wave packets in. But at the end of the day, there are no poles that depend on the kappa tildes. So you can Taylor expand in the kappa tildes. The amplitude is real analytic. And this allows you to think that at least for staying within the MHV subsector of celestial CFT, these dual operators might also be real analytic in the kappa tildes. So this is the ansatz that I'm going to make. I'm going to decompose. I'm going to Taylor expand. Say O plus, let's do the gravity case. O plus Z kappa tilde associated with some null momentum with spinor variables Z and kappa tilde. So kappa tilde is kappa tilde 1 dot, well, and kappa tilde 2 dot. I've just lowered the indices, but for convention's sake. Taylor expanding this gives us sum over some integers mn greater than or equal to 0. Taylor expanding in kappa tilde 1 gives us kappa tilde 1 to the m over m factorial, kappa tilde 2 to the n over n factorial times some coefficients. which I am going to think of as soft operators. So let me denote these coefficients, these z-dependent coefficients, as w square bracket mn, denoting which order I am at in the Taylor expansion, and then they are fields that depend only on z. So if you assume, it's a very reasonable ansatz in the MHV sector, that the operator is real analytic in the capitals, then you can expand this operator in terms of chiral soft currents, which is probably weird because Prahar explained to you that we have to expand stuff in terms of principal series operators. So what I'm trying to explain is that at least within the MHV sector, you can do a Taylor expansion rather than an expansion on a complete basis of states. That expansion that Prahar showed through the Mellin transform works all the time, more generally in other LST sectors as well. But here this is very convenient because now we have chiral currents. And as soon as a CFT has chiral currents, and same with celestial CFT, as soon as any CFT has chiral currents, what do you conclude? Well, in a CFT, well, at least in the normal version of a CFT, chiral currents are d bar closed. They are holomorphic in Z. And if you think of Z bar as time evolution in radial ordering, then the chiral current is a conserved current in that language of radial ordering. So that means that the WMN chiral currents generate symmetries of this OPE algebra of the celestial OPE. Let's figure out what their algebra is. So we have the hard algebra. We have the OPE of two hard modes. How do we figure out the OPE of the W's? By Taylor expanding both sides, right? It's a very simple calculation, which I trust you will all do because you're all good students. Or we can do it as an exercise if you like. You Taylor expand both sides of that hard O++ O++ OPE in kappa 1 tilde and kappa 2 tilde. The right hand side is a function of kappa tilde plus kappa tilde j. So you have to sort of do a binomial theorem. And when the dust settles, and you compare coefficients of kappa tilde 1 dot to some power and kappa tilde 2 dot to some power, you will get the following OPE algebra of the soft currents. WPQ of Z, WRS of Z prime goes as PS minus QR over Z minus Z prime W Q plus R minus 1 Q plus S minus 1 evaluated at the second point. And okay, so there is a little bit of a check. You have to check that OP is associative, but more or less, and that OP is associative, but more or less that is just Katz-Moody style OP, so they are associative. This OPE then is associative again, and it forms a symmetry algebra of that hard OPE, in the sense that if you act with a W current on the hard OPE, then this will equal W O plus plus O plus 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 O plus plus W O plus plus, where I can draw some Wick contraction notation to indicate that I'm taking OPEs. And in this sense, the W's form symmetry currents of that OPE algebra. And this algebra is known as the loop algebra of the wedge subalgebra something called little w 1 plus infinity. And this seems to be what has made celestial holography more popular recently. So I thought that I should give you an idea of this before I go to twistor space and show you how this naturally emerges from twistor space through some very simple model building. But okay, there is a gluon case which I can write down in a sec. In the gluon, any questions about this? And I'll just write down the gluon result and that'll be fine. If anyone wants me to derive this, I can. It doesn't take too long. But we can do it in the discussion session, I guess. I'll write down the gluon case. In the meantime, if questions come up to your mind, you can ask. So, take another board. Do not take that board. So in the gluon case, you do a similar Taylor expansion into some Kac-Moody style currents. Factorial n factorial J A M N of Z. I'm using the notation capital J to make it feel like a Kac-Moody current. And now you can compute the OPE of these. EQ RS of Z prime. And this now goes as the structure constant PS minus QR now gets replaced by the structure constant of the gauge group. So you get JC P plus Q, P plus R, Q plus S. The left indices add, the right indices add, evaluated at Z prime. So that's the second algebra. That's the gluon algebra. And I didn't really focus on explaining exactly why I'm calling this a soft expansion, but that's more or less should be clear by the fact that you can take kappa tilde and you can write that as some energy times 1 Z bar. And then this is sort of an expansion in omega and Z bar. So in that sense, it's a soft expansion. But it's much cleaner to think of this as an expansion in kappa tilde because then it's invariant under how you decompose kappa tilde. That's the gauge theory case. In the next lecture tomorrow, I will explain what the geometric interpretation of W1 plus infinity is and how it's naturally realized through some OPE algebra living on the twistor lines. And in the other case, I'll probably see if I have time. Okay, thank you. Sorry for going 12 minutes over time. Any questions?